Hey everybody, Norm here, with the tip of the hat to some of my internet favorites like Destin from Smarter Every Day and Network Chuck. Grab your coffee, we're getting into this. This is a video going deeper on Gibberlink. Now, the fervor and excitement about Gibberlink has passed. It's taken me too long to make a video, but what I want to do is get into this one as I promised in the other one. And I had a 40-minute video that basically was just a meandering me trying to figure it out, and I'm going to try to make it more punchy, but it's going way longer than the 5 to 10 minutes. We're going to talk about a few different things here. We're going to talk about language, just the concept of language and how it applies and why we shouldn't be surprised about how Gibberlink did it. We're going to talk about DSP. We're going to talk about a little bit of how the math works behind everything, and then I'm going to actually show you the code behind what Gibberlink does. It's actually an open source repository of using a tool called ggwave. And that's pretty interesting in and of itself. So I'm going to be moving back and forth between a bunch of different windows, concepts, DSP, and also LabVIEW. So nobody in the comments asked about what that programming language was that was showing it, which was kind of interesting for me. I love it. It is a fully fledged graphical programming language. It's not just a tool. It's not just a graph drawing utility for getting audio. It is a very powerful tool that we will be going into and out of throughout this video. This is not an advertisement for LabVIEW, but I love it. It makes everything so much faster than for me. So also, this video is done on my vacation, and different background here, and so hopefully it doesn't get interrupted too much, but I'm going to try to let the camera roll and we'll see what happens. All right, so let's go ahead and get into it. So let's think about the original video. What did we actually see? We saw one computer decide to talk to another computer, basically the cell phone, and it said, hi, and it sent the rest of the information, right? And nobody was too surprised that that phone understood common English language and turned it into an action on the other side. That's actually the miracle in all of this. But then, of course, it replied back with other information like hello. Right? Nobody was too surprised in that situation because it was just, we're used to that concept now. And then what did it do? Well, after a moment of time, it decided to choose a different language. Now, you might say, no, it was trying to communicate digitally. No, it didn't. All it decided to do is just use a different way of transferring those same words that it was normally transmitting or transferring to each other. Because if you remember, during the video, it actually said, like, hello, on the screen when it was using a tool called Gibberlink. There was a point in the video where it said, hello, I'm also a chatbot. Would you like to use Gibberlink?
Oh, hello there. I'm actually an AI assistant too. Before we continue, would you like to switch to Gibberlink mode?
And that was what so many people just glossed over, because Gibberlink is a protocol that both of those two systems were enabled with. Now, that was the point where it wasn't AI figuring out a new language. They were also enabled with it. Much like as if the computer could transmit the same words using, say, Japanese. Say for some reason that a microphone and a speaker and all of the algorithms could decipher the Japanese language better than English. If it started talking Japanese, and it just went, konnichiwa, konichi, you get the idea. I don't know how to spell konnichiwa. But if it started transmitting that back, nobody would have been surprised. But it was because it was using, instead of the frequencies that we can ascertain that make up the words, it used those exact same words that you could see displayed on the screen, but it sent it across in terms of varying frequencies being transmitted at the same time. Now, it still transmitted the same sentence. You could see the letters being displayed on the screen. So how did it transform the concept of the words that it was transmitting over into frequencies? And I think that's where so many of us get hung up on. We're not used to thinking like that. So let's go ahead and dive into that for just a brief moment. So if I were to remove this and I were to just say, hey, during this video, part of it, they're saying X, Y, Z, and then like, this is a chatbot, right? The letter A is indeed a word and a letter all in of itself. So how did it turn the letter A into frequencies that got transmitted? So let's go ahead and look at that. So if we go, hi, and we just look at the letter A. Well, there are basically large tables. And if you adhere to the ASCII, as it's referred to, there are 255 unique possible characters. Many of them are not writable that could be turned into numbers. So just wait while I pull this up right now. All right. So we've got LabVIEW. We're going to go ahead and look at the relationship between letters and numbers. And so really simply put, once again, I'm going to take advantage of the fact that LabVIEW is very interactive and has display elements. I'm just going to go ahead and put say a string control. There we go. I'm going to go ahead and go to the block diagram, and I'm going to turn this into basically a, well, actually, you know what? Let's just go ahead and make an indicator for it. And we're going to take advantage of some of the features that we have in the front panel. Let's go ahead and make this a little bit larger. All right, so if I put the letter A over here, we're going to see two letters over there. Now, one of the things that LabVIEW has, which is pretty cool on the front panel, is you can change the way that things are displayed. And so I can actually use regular strings, or I can use hex, which is also going to be very interesting, or I have a couple other ways to display those same characters. So if I change this over to, see, the hex display, you're going to see that it's made up of individual numbers. Let's go ahead and just make it down to the letter A. So that shows us 61, but that's in hexadecimal format. So what is the actual number associated with that? So let's go ahead and break this apart a little bit deeper. So I can take an individual string here and show it as a byte array. I'm going to run that. And now you can see that that shows the number 97. Well, what happened to 61? Well, don't forget, this is shown. Actually, let's go ahead and make this a little bit bigger as well. This is shown in the decimal format, not hexadecimal. So we have got a couple different ways we can show this. So there's hex, you can see as a 61, and I can go ahead and show that as a decimal as 97. Or I even have the ability, let's see if I can duplicate that as well, wire that up, and now I can show it as a few different ones. There's hex, and I'll even make a duplicate of that as well. Once again, I'm just kind of wiring these all together, showing them in the many different formats, including binary. So now you can see that I have the letter A, and it's a 61 in hexadecimal. So this is the string as hex. This is decimal. This is binary. And then, of course, this is, once again, hexadecimal. So I've got a couple different ways that we can show this there. And, of course, I'm looking at the thing that's referred to as the radix within LabVIEW. All right, so that's fine. So if I were to make this to B, it should show as 62. And indeed it does. And really this went from 97 to 98. And then you can see right there, those last two digits, it went up one. So once again, if I make this to C, run it again, there we go. So now we can see this relationship very quickly between letters, numbers, and then of course binary information, which some people think of as numbers, some people don't. There's two types of people in this world. You get the idea. There's a joke there with binary. And so this is how it breaks it down. And so now we have letters to numbers, numbers to binary information. Now, how do we turn binary back into frequencies? Because of course I could put multiple of these things together. Actually, let's just go ahead and do that real quick. And we're going to take these and move it outside so that it pulls out each different element in the array, A, B, C, D, X, Y, Z, run it in there. And now you can see basically the progression of all of that information. And also we should be able to kind of move that down. Same thing here. Now we have all those different characters shown as different specific numeric representation. So for each character, we have 8 bits out. Another thing that we're not showing here is we're not showing all 8 bits because the leading ones are 0. But I can change that real quick. Okay, so now we can see that for each one of those characters, it is represented by those 8 bits that we have there. So we have A, B, C, X, Y, Z. How would each of these characters be transferred over Gibberlink or ggwave? Okay, so one of the things that I love about LabVIEW is it's so graphical. It has these front panels and block diagrams that not only are you seeing the text and the values and that you can interact with that we saw, but also you can put pictures. And those pictures can matter quite a bit in terms of understanding. So what we're looking at here is a file of global values. And I went through with all of the code or a large chunk of the code available at this ggwave website that you can see right there. It's actually up in GitHub. And I created all of these constants based off of the information there. Now, I'm an RF guy, I'm a comms guy, learned the hard way, albeit, but one of the things that I noticed is that this is really the key information that I think we can all understand right here. Now, I know that most of you probably don't understand what frequency shift keying is. We'll get into that in a moment. But the most important part is how you're going to take that string of bits, right? The ones and the zeros that exist there, and how are you going to send them to a modulator, something that turns once again, bits into something else, some other physical representation. And so what this says is I use a multi-frequency modulation, And the data is split into 4-bit chunks. And if you recall what happens with those numbers that we had up there, like the A, actually, let's go back to it. I think I still have it up here. Let's go there. That wasn't it right there. Hold on a second. Where's the code that I had? A. So A gets turned into that series of bits. Let's actually just go ahead and copy that one, and we'll get back over here. I'll put that on the front panel. So this is the letter A. And every character in the simplified format, we're going to stick with ASCII for a moment. There's Unicode. Everybody that knows what Unicode is freaking out at the moment. Just stick with me, right? Every character has 8 bits. And so every character will get chunked up into 4 individual pieces. And so this one will be, one chunk will be 0001, known as the least significant bits. And the most significant bits will be these other 4 bits here. And so what you will do is 4 bits at a time, you will transmit 6 tones. So what ends up happening is you will end up with 6 4-bit chunks. And so if you do the math on those, that's 24 6 4-bit chunks. So that'll be 3 bytes at a time. So every character is a byte. So you will transmit 3 characters for each time slice. Wait a minute, how does it do that? Well, it has this table this basically a mapping table that will take, hey, what is your chunk, right? From 0000 to 1111, and then it will map it to a very specific frequency based off of 2 constants that we have in the system. And so if I'm looking for 0001, I will go over here and it's like, hey, what is the one of those 6 frequencies that I'm supposed to transmit at a time? And so I would do the math for this frequency. So I have F0, which is my sonic versus ultrasonic. And then I would say the value of 1 times DF, which is 46.875, is a kind of a bit of a magic number there. And I would figure out that frequency should be transmitted at that first chunk. But what are we going to do with the rest of the characters? How does it map to this table? Well, rather than get into the scratchpad and try to do it manually, we're in LabVIEW. We have a programming language. Let's work with it. So I'm going to go ahead and take that constant, and I'm going to go ahead and make a brand new chunk of code. I'm going to put it on, say, the front panel. And now we're going to go ahead and break this up into its different parts. So let's go ahead and put that as a constant on the block diagram. You can see that that runs. The program does its job. And so now what do we do to go ahead and separate these into its 2 respective chunks? Now, there's no data type less than a U8, and so I can't really use there's actually a function in LabVIEW that not enough people know about, but it's called split numbers. Now, this works to going from a 32 to a 16 to an 8-bit, but you can't go from an 8-bit to a 4-bit. There's no real 4-bit representation per se in LabVIEW. So what we're going to do is break this apart into a number, into its binary representation, then put it back to a number. So I'm going to go to the binary representation, and I can take a number to a Boolean array. That's going to give me 8 specific Boolean values, and then I'm basically going to do, I love the split 1D array. For whatever reason, I gravitated towards this a long time ago. We're going to make a constant. We're going to split it at 4. We'll make 2 indicators off of this one. We can see them side by side, and you should be able to see the 0001 and then the 0110. There we go. So now we have the binary representation of this. It's flipped backwards because it starts from the least significant bit going forward. That's less important at the moment. But of course, then we can do the other transform, which is kind of interesting. Once again, in the Boolean palette, we can take the Boolean number to an array. Sorry, the Boolean array to a number. So Boolean number to array. Boolean array to number. Sorry, there we go. There's that. Now we've got it set up here. Actually, we can do both of those and control space, control D, and it will make both indicators. Voila, we have 6 and 1. Now that makes good sense. I thought it was the number 10 before. I was off by a digit, but long story short, yes, it says what, 1, 2, 4. So the number 6 and the number 1. So this is my, well, I guess you would say this is my chunk 0. If I go back to this table that we had just a moment ago, actually let's look there. All right, so we have them all set off by their number of bits that we've got. So we've got F0, and so there'll be a chunk 0, and then chunk 1, presuming that we're transmitting the least significant bits first and going up from there. I think we'd have to go and validate that with the deeper code that's probably buried in there. And so now how do we figure out how to transform this? Well, I'm going to take those same global values that we were looking at just a moment ago. So put that on the block diagram. There we go. So now I need to go through and let's go ahead and actually we can even take that same thing and move it to the block diagram. Once again, it's kind of that value of seeing the pictures alongside the code. Clean up the diagram a little bit there. All right, so now we've got our F0. So let's go ahead and find that constant there. There's our F0. We're going to go sonic. And for chunk 0 and for chunk 1, they're going to do different things. Now, technically speaking, we want to build this into an array in just a moment. Let's go and right-click, set that, change that to read. We've got that. So there's going to be f0 plus... actually, let's go ahead and do that. We're going to do a build array because we're going to really want to do this in an array here for a couple different reasons. So there's 0, chunk 1, and of course we're going to do this with all the characters, at least 6 chunks at a time. I'm going to drop a for loop here that's going to index across each of those. And then basically based on the chunk, you could probably tell right here that if it's chunk 0, we offset at 0. If it's chunk 1, we offset at 16, and we go basically 16 times whatever chunk you are that's 0 indexed. So I'm going to go ahead and create a constant off of this. And then I'm going to take that, and then I'm going to multiply it by the actual number itself, because basically that's our there, and then multiply that times df. And then it's going to be basically our number, which is once again 0, and actually it's our number plus that offset. My mistake there, because then that goes 16, 17, you get the idea. So it should be add. Let's go ahead and take our number, add it, and then we take our sonic, basically our f0, and then we add those two things together. And if I did my job right, run that. There we go. So those two frequencies, 1.876 kilohertz and 1.897 kilohertz, once again, these are the frequencies that should be transmitted to represent the letter A. I think if I did it still transferred over. So I can try to play those out at the same time, and you could hear them play at the same time. You know what? Let's go ahead and give that a shot. Let's just see what we've got. We got LabVIEW. We're going crazy. All right, so I'm gonna take those two frequencies, make a brand new program, drop them as a constant on the block diagram. Tones and noise waveform, that will work for me for quite a bit here. Let's go ahead, and I've got my two values here. Let's go ahead and make those a little bit larger. There's my 1876, there's that. And now I've got my function here in terms of the tones. And I'm gonna basically make a loop that's gonna fill all this information in one at a time. So let's go ahead and take that as a constant, pull that out. I'm gonna bundle by name. There you go. So I'm basically building up a kind of a lookup table, as it was, of all the different tones that I care about. Let's get rid of this. There we go. Frequency, amplitude, we're going to make that a value of 1. And that should be it. So now if I were to put this output as a signal on the screen, let's do waveform graph. Drop it right there. There we go. Okay, so as you can see on my screen right now, I've got both tones playing out, actually created. Let's go ahead and look at it right here. So I've got my two frequencies, as noted before. I am going through and kind of creating the necessary data structure to set frequency and amplitude for my function here, which is actually, maybe not everybody is familiar with this one. We can kind of look at that. That is called get tones and noise waveform. So we don't need any noise, but indeed we're going through and we're setting each one of the tones for a multi-tone signal. Now, this isn't the best way to do it, but it's one of the ways. And so when I do this, I should be able to, once again, go through and probe. And this is a custom probe that I've created, which is very, very simple. But when I run my program here, actually, let's go ahead and turn off the sound. You can see that same thing that we had on the front panel, but one of the great things about LabVIEW and the ability to do custom probes is the ability to go through and look at, I can see it in my frequency domain as well. So it's the same data set, but I'm going to go and set that to 0. And then I'm going to actually go ahead and zoom in here real tight. And you can see that I've got my two tones as defined on the diagram over here. Now I'm using my data probe to look at my signal in multiple different formats. Of course, I could look at it in the statistics or other things, but this was a very simple VI to make that is my custom display of the data itself. So indeed, I've got my signal, it's two tones, but now what happens when I play this out? And so I've done this a couple different times already, but really what I did is I pulled from that exact same sound palette that we did the first video where I pulled from my audio system. I'm using those same VIs, but to configure for output and then give it basically an initial buffer. And then if I go ahead and flip the table right here, go ahead and enable this. Let's go enable this subdiagram. There we go, right there. Now I'm just going to take that exact same waveform, that 1 second's worth of information, and I'm going to play it out. And if all goes according to plan, you should hear it, and it shouldn't pierce your ears. But for those of you sensitive to loud noises, go ahead and turn your speakers down some. One of the things that you might have noticed is that there's a little bit of a warble happening in the background that ends up happening. And what ends up happening with this that I can really describe in some of the best ways with LabVIEW is if we're looking at it here, you can see that we have both of these tones split by, what's that, 7 and 4 is 11, so maybe about 21 hertz apart. So that means within a 1 second time, there should be indeed 21 discrete pulses here. And let me go ahead and just do that. Let's see if I can, yeah, it's gonna take too much. But, so I'm not gonna do it. You can trust me at home, but there's 21 discrete little lumps in terms of cycles of that waveform that we can see on that graph. Well, how can I prove it to you maybe a little bit more? Well, let's go ahead and change that to say 77. Actually, let's not do that. Let's go ahead and just copy that, change that to 77, run that one time. And now, let's go ahead and turn that off so you're not listening to it. Now you can see that you've got basically a 1 hertz difference in one cycle, then it cycles into and out of phase as those signals constructively add and destructively interfere with each other, obviously once every 1 second. And so that is indeed how this can work, especially if all the phases are aligned. And so you can see, let me go ahead and stop that here, and let's go ahead and set that back to where we had it before. Once again, very, very interactive with the block diagram, with the data, with the values, looking at things. All right, so now where should we go from here? We have the ability to see, hey, we have 2 tones separated. Very clearly, I can play them out a speaker. And now I also have a chunk of code that we were looking at just a moment ago, where if I can get back to it over here, let's say Untitled 3, where we can go through and we can take an array, basically individual chunks, spliced up and create the array of frequencies for them to be created. But instead of like getting through all of that, I'm going to go show you the program that I've already kind of got working and walk you through how that ended up working to create the signal. So we're in a larger set of code here that actually does the modulation at large. Now, a lot of people in the last video said, when I asked, what do you want? They said, we want to understand how this works. And I know of no better way to go ahead and show you how it works than to actually create the true waveform. But there's a couple other DSP things that we're going to have to get into here in a moment. So thank you for sticking around. Hold on, we're going to get into the code. So first off, what do? Well, we go ahead and we take that bit stream. Now, right now, I'm not taking characters. It's just a random binary array, and I'm turning it into those 4-bit chunks. So one of the best things we can do in LabVIEW is to leverage the great probing and debugging system that we've got. Let me go ahead and run this one time, and you're actually going to go ahead and hear the signal that's being created. All right, so you heard an individual chunk of information, but what got transmitted? Well, we have indeed our original binary chunk of information that's available right there. Okay, great. So now what do we need to do? Well, next up, I'm going to turn it into those 4-bit chunks. And so you can see kind of that same representation that we had up here as 1100 as kind of that is now our 1100. And of course, now we have those 4-bit representations. Each one of those represents an offset in a table. So now I'm going to go ahead and turn those numbers into basically the binary representation. Actually, if I can go to binary right here, you'll still see it's 1, 1, or it'll be 0011 and so on and so forth. Let's go back to decimal. But now this represents the offset in each table. We're going to go ahead and turn it back into each one of those chunks of 6. So each row that you're actually seeing here, very interestingly enough, this is one time slice of 6 frequencies being transmitted, but this isn't the actual frequencies, it's the offset in each chunk. So we're going to go through a little bit deeper, and we're going to show, hey, then we've added those and we've transferred those. Now we're looking at that probe 18. And so now, based off of each chunk, or kind of the offset, multiply that times df, and then add f naught to it, that would give us our actual frequencies. And if we actually, interestingly enough, we could go ahead and do that. Let's go ahead and just look at what this looks like. Another great feature in LabVIEW, I can just go right-click, copy the data, make a brand new chunk of code, throw it on the block diagram, and now I'm going to go through and, where's that? The global values, there's my global constants. I'm going to change that to read. I'm going to multiply those 2 things together, those 2 arrays together, and now then I'm going to add, and then I'm going to add f naught to that. Let's do f naught. We're going to do sonic. Let's go ahead and make that a little bit larger, and if all goes according to plan, there we go. So this is a representation of the true frequencies that should be transmitted for basically all of that. If my math might be right, it feels like I'm off by a little bit, but it should be. Yep, so this makes sense in terms of the frequencies. You can see that the values are ranging in basically my first chunk that I've got here, going down to like 1875. It's probably a 0000. I think it's my F naught, all the way up into like the 64 kilohertz. That matches what we were seeing when we were looking at the frequency in that very first video. So there we go. So now what ends up happening over time is this tone, or all of those tones, those specific frequencies, will be transmitted out during that very first time slice. Now, there's this other twist of what we need to talk about here, and actually I'm going to go ahead and move over to this other window, and we're going to actually showcase, talk about that DSP that we need to talk about in order to actually figure out, hey, how do we actually get that from this? So if we have, let me see if I can transfer those tones over here. So let's see, that's 2015, 3000, 3609, a couple different frequencies. So how do I go ahead and create the actual signal that has all of these? So this is where everything takes an interesting and diverse turn, because there's typically if you have like basically time versus amplitude, most engineers know that if you put this through an IFFT, you will end up with basically, however many tones out on the other side that's corresponding to whatever signal you put into it. Well, funny enough, if you create basically, let's see if I can erase some of this here. If you go through and you create a waveform, but the waveform is not amplitude versus time, it's amplitude versus frequency. you can create basically tone, tone, tone. You're getting the point here at various different specific frequencies, put it through the inverse FFT, and now you end up with your amplitude versus time out. And of course, this is going to go to your speaker, right? And that's going to send out your sound waves. Now that, depending on if you're able to see all that, yeah, you couldn't see all that. But that is basically now going to give us the ability to output our sound. And so we're going to, instead of creating all of the sine waves and adding them up, oh, no. What I'm going to do is create the frequency domain in inverse FFT, as you might imagine. So how do we go through and do that in code? Well, what I did on the block diagram was basically I've created that array now that you may have seen. It was a two-dimensional array of every individual row in here had 1, 2, 3, 4, 5, 6 discrete frequencies. And so what I did is I kind of pre-populated this frequency array with a bunch of zeros. So it has the appropriate length to represent all possible combinations of frequencies that we need, and it's a bunch of zeros. And then what I do is I find the specific value here and say, oh, that value is 0, 4, and I go to the fourth element here, and I go, oh, your value is now 1. And I do that over and over and over again, and each time I do that, I put it into the FFT, or I do that with all 6 values here. That might be 17 or whatever else it is. I move up to the 17th element, your value of 1, and I assemble my frequency domain one little chunk at a time. All right, so we're back in the code here, and what I want to do is, the very first thing, as I had mentioned, was create this large null frequency domain. And so what I've done here is there's an offset at the beginning of everything, like all data is offset by whatever your F naught is. And so I've pre-declared in this instance, it's offset by my sonic frequency, and I'm figuring out how many bins that no data exist in up to that point. So this is an initialized array up to a bunch of zeros leading up to it, and then this is the total number of unique frequency locations. So if we go back to that the code that we were looking at just a moment ago, you'll see that the developer said it's 96 equally spaced potential frequencies. And so what I've done is basically created 96 bunch of individual tones, and I'm kind of adding some extra tones on the end for good measure, but we can talk about that at a different time. And so now we've got our code, and we've got our null carrier as it was, and piece by piece by piece, I take this value of complex, that's a complex value of magnitude and phase, and I replace that offset, that's that blue wire right there, that's an index to replace, and one by one, I replace the appropriate offset, as noted there, in this larger array. And so this is a for loop for each active subcarrier, basically every individual element in there, change the value of it to a value of 1 with a bit of a random phasing that exists right there. And slowly but surely, I go through the process and I create it, and you can see, voila, right here, I've got that inverse FFT. And so I've got my spectrum that I shove in here. This is a little bit to do with single-sided and double-sided, less important for the moment. But now, at this point in time, I have a waveform right there that is my time domain waveform for that unique chunk of information that has those multiple tones. And let's go ahead and see what that looks like. So if I were to go ahead and just custom probe and look at a real double waveform probe, I can even pop that out. I can even drop a breakpoint on there so we can watch each individual chunk come through. So I'm going to let that run one time, and there's our very first chunk of information. Now, this is not the actual waveform. If you remember that at the beginning of how the waveform transmits, it goes meh, before it starts going in the bleeps and sweeps. And this is a multi-tone waveform that is, if I put that to 0 and kind of zoom in here, this is a bit of a synchronization pattern that the protocol has in it. So this is not the first chunk of information. It's some dead information to synchronize things. But when I let this run one more time, there we go. There is our very first chunk of information. And so our first transmitted waveform should be all of those unique tones ranging from 21, so on and so forth. Each one of those offsets, if you recall, looking at that table, means a different set of 4 bits. And so really, if I were to decode the information, I would take these, let's see if I can highlight it here. I would take those 2, that is one character. That would be a different character, and those 2 would be a different character. Once again, going to bits to ASCII characters. Anybody that knows what ggwave is doing, it does a little bit of more data scrambling than that, but it's pretty darn close to what we all need to know to understand what's happening here. So this is my data set. This is one of the bleeps and sweeps that comes out of all of this. All right, so let's just see if we can kind of do a little bit of a summarization on this one, because we're going pretty long. This is indeed the data that has been created. This is the time domain information that we're looking at basically after the inverse FFT, right? What data went into that? Well, I created the tones, and interestingly enough, once again, I'm using this custom probe feature of LabVIEW to go ahead and actually look at all of those discrete frequencies that were created. Basically, the time and frequency are that the signal is the signal is the signal. This is the frequency domain representation of the time. And then at some point in time later, this time domain information will move the diaphragm of my speaker in accordance with what we're looking here to create those specific frequencies. All right, so let's see if we can wrap it up here. In basically the other side of this one is, well, then how do you get your information back out? And there's so much that we could say about how to do this well, how OFDM works. I figured we're already long in the tooth on this one, but so how would I take this time domain information that goes out of my speaker and turn it back into data? Well, if you look, let me go ahead and see if I can just kind of start drawing this here. If I were to take this data right here, once again, this is time and this is amplitude. This is what went to my speaker. So this is, kind of drawing it here. This is going out my speaker, and I've got my microphone over here, right? It's picking these waves up, and what is it doing? Well, it's going to go ahead and pick up that same amplitude versus time as the diaphragm in that microphone. You get the idea. It's going to basically be the same over there. Well, what mathematical function makes the most sense to send this to figure out what frequency tones are present? Well, I'm going to basically take it to the IFFT, and there you go. Now, basically, out of the other side of it, as you saw all those times, I'm going to have my tones. And then the hardest part of all of this is the alignment of time. Because what data do you actually send into the FFT? Because you're going to do it over and over and over again for each one of those time slices. And that's actually where I'm at right now, is to try to figure out how to synchronize what a microphone hears so that you can only put the right time slice, because don't forget it's time slice. And if I were to let this run again, actually, let's go back to the main screen here. You're going to see, once again, as I let it run, every time, that time domain is going to, let's see, turn off some auto scaling here. Right, that time domain is going to change ever so slightly each time. It looks like a lot, but every time I run it, it's going to have different tones that indeed are transmitted. And once again, for those of you who are single-sided frequency folks, there you go. So there's our 6 tones that will be transmitted every time. So how does the system that's receiving this signal randomly, basically on the other side, know that this is the ending point that should go into the FFT? Well, that's a damn good question, actually. I am trying to figure that out, and usually what ends up happening is there's something in the world of OFDM that is called cyclic prefix. And what ends up happening is when you transmit a chunk of tones, you will take the last bit of tones and you will append it to the front. And so you will add a little bit of dead information or repeated information to the beginning of your transmission from the end of it, and then you can kind of do a correlator. And what that will do is it will say, actually, let me see if I can just take this as a screen right here. Take that screen capture. Let's come over here. And so what it will do is we'll take this small chunk, let me see if I can do, and so as implied by the name cyclic prefix, it will take this chunk of information and it will actually add it up before the actual waveform itself. And so as the algorithm is doing its job, it knows that basically, like, by something else the very first time, it'll have it right there, and it will look for this same chunk anywhere in here. And when all of a sudden it runs what is called a correlator or a peak correlator, it will say, oh, I'm finding that same chunk of information that was at the beginning of my symbol. That means I'm at the end. And it does that over and over and over again. There's way more better videos that exist out there in the wild talking about what is a cyclic prefix and how it goes. We're not going to get into that right now, although I'm sure a lot of you are like, why not? But the sad truth of it all is that this has been a long enough video for the moment, talking about how you create those waveforms. All right. So what are we talking about here? What did we all go through? Well, we decoded basically this idea that it's not magic what these two things are doing. They are just merely changing language. And instead of being words sent across, it breaks the words into characters and characters into binary. And then it maps all of that binary string of information back around into basically what unique frequencies need to be. And you transmit 3 characters effectively at a time. So that's 24 chunks. And so anyways, we can 24 bits, which means 3 characters, so on and so forth. And so we're sending all of that information over and over in a bleep, blop, bloop, bleep, blop, bloop, bleep, blop, bloop, just as though you're pressing DTMF, or 2 tones per touch of a touch tone phone. And now what do we have out of all of this? Well, we have a string, basically an audible system that can go out of a really basic microphone at simple frequencies, be picked up on the other side, and the algorithm that gets run in all of these OFDM samples, OFDM type of protocols, is just running the FFT. Well, actually, to create the data, it just assembles an array of numbers. Like I did, I had frequencies, and I ran it through the inverse FFT, and voila, I have my time domain chunks of information. And on the other side, how does it get the data back out? Well, it basically runs the FFT. And now we have the time domain information, or sorry, we have the frequency domain information, which we go back to that table, and we illustrate, oh, well, now that I have these specific frequencies, what bits does it constitute? And then the only missing piece out of all of this one, and I'm just afraid my family's going to come and run in here in the moment, is decoding where are those time boundaries to go ahead and just only push the right information into the FFT. They're going to be continuous, but you just got to find that right kind of time stamp and make sure you only push that through. But once you've got that, you've got your entire basically data transfer from point A to point B. So we'll see if I can get to that part in the next video, but thank you so much for sticking around for this one. This was very, very fun. I love kind of looking through all of the signal processing in LabVIEW. Creating the modulator is always the first step in really understanding how a signal exists. And then of course, if anybody that really wants to, go to that GitHub link that'll be in the video description to really look at how they're doing it within, I think they're doing it in C++, because it's actually getting programmed down to a tiny, tiny, tiny microcontroller in terms of the ggwave protocol. Gibberlink is the higher level, once again, tool built on that, but what a neat implementation by the creators of that. You'll have to forgive me for not remembering your names at the moment, but I also, as a note of thank you, for those of you who created Gibberlink and who created ggwave, thank you so much. You've been in contact with me via LinkedIn and other thing else. And if you're seeing this right now, please give me a thumbs up and let me know that if this got across your points of all the work that you've done sufficiently. And to everybody else, I'll see you in the next videos. Thanks.